go. Ready?
Yeah.
So the where this idea is coming from is that last winter, Mary and Karen and I gave a math night for about 50 to 60 parents up at Browns River. And the feedback from that night from some of the administrators that were there and actually some of the classroom teachers that were there was that we should give the same presentation to the math committee. And so we did. And the feedback from the math committee was everybody should hear this message, not just parents in the math committee, because it's more about core beliefs and less about math games or math tips. And so that's kind of where it's coming from. And so we're taking actually an hour-and-a-half talk, and we're going to try to trim it down to slightly under an hour. And so that just know that there's a little bit more in the full version. Yeah.
The reason we wanted to share it with teachers was because if parents went and then they referenced something in it that you might want to know what that was, and we're like, oh,
closing
good
the loop.
idea.
Yeah.
Okay, yes.
Everybody's in on the conversation. The neat thing is that
we weren't trying to subvert anything or anything, just like it evolved from.
And a lot of it is summarizing some of the big philosophical shifts that we have had as coaches through the work that we've been doing in schools and through the research that we've been reading. And so, there's going to be a sense of familiarity, but a more summarized, succinct version of familiarity.
The last piece is that there's a parent night December 6th in this part of the
building.
district
here.
And so it's something that parents will be hearing and have the opportunity to come to and see. And
How is that being advertised?
Flyers are going out soon.
Flyers are going out really soon. Yeah.
You can put it in our
And you can put it in the newsletters.
Yes.
Mark will get it first and then send it your way.
December 6th, you said?
Yeah.
Time?
You want me to wait till
6 to 7:30?
6 to 7:30.
Hour and a half?
Mm-hmm.
Yeah.
With parents.
Oh,
And
6 to 7:30.
barely fit it in.
Yep.
We do it really fast at the end.
We start cruising. That's why this is here.
Mm-hmm.
And is it for all
Parents in the district,
all grades?
not
Yeah.
kids.
All
K-8.
grades, yes.
K-8.
Mhm.
So I want to, just because of time, I want to get rolling. So this is kind of where we're going to, is that there's a lot of feedback in the general public right now that math has really changed. And they say words like new math. Oh, you're teaching that new math. Why doesn't it look like it did back when I was a kid? Why is it so different? And so what we're kind of focusing tonight on is that math actually hasn't changed. There's no change in math. Actually, math is exactly the same. Math is math, but our core beliefs about math has changed. And so what we want to address tonight is what is the research that has happened over the last years that have caused us to change our core beliefs about math so that math instruction looks a little different. Because even though math hasn't changed, math instruction has certainly changed because of our core beliefs. And so the research that we've looked at a lot and spent a lot of time, and there's practitioners around the country right now and the world that are really looking at how kids are learning, what are the progressions and learning patterns in math, and then most recently they're starting to connect this to brain scans. And so a lot of what we're talking about now is not just backed up by research, it's also backed up by science. Ooh. So what I want you guys to do is take a little scrap piece of paper, and for the teacher version of this talk, I would like you to cut it, like draw a line straight down the middle, and on one side I'd like you to write, what do you think, how do you think the general public or parents would answer this question? And then on the other side, how would you answer this question? And we did this at the parent math night. So on one side, what does the general public
Did you ask them to say what they thought?
No, just for them it was just the general. What do you think? But for you teachers, you educators, what do you think the general public, how do you think they'd answer this question, and how would you answer this question? Oh my.
I don't mess around. If you would like one that makes you happy.
One that
Yeah,
makes you
well, I
happy.
say on.
Okay. You don't mess around either. Got it.
Sorry, I heard many teachers.
Color their sharps.
She came to the interview with.
We're meant to be.
Take like 15 more seconds. All right. And what's one thing you thought that the general public believes about what it means to be good at math?
They do it easily.
What does that mean?
They don't have to try hard.
Oh, like effort.
Yep.
Easily connected to effort.
Yep.
So if you're good at math, it's kind of effortless with
Yep.
your computation. What do you think, Rebecca?
General public might think they get right answers all the time.
Ah, accuracy. So it's effortless, there's accuracy. What do you think, Angela?
They're good at their facts.
They know their basic facts. Which ones?
Multiplication.
Multiplication facts, the times table. If you know your times table, good at math. Mary?
Fast.
Fast.
Can get answers quickly.
Karen?
And use algorithms.
Can use algorithms. The same
Solve
ones that they
problems to
knew.
use algorithms, yep.
Sarah?
I have that someone told them once they were good at math, or like someone's reinforced that within you.
Let's flip to the other side. What does Anna say it means to be good at math?
I said that they ask questions, meaning that they are like they're curious and they're inquisitive and they're like, well, why does that work? Sort of questions.
Get it kind of connecting to deeper meaning, like deeper understanding, or specific just to asking questions?
Specifically the thinking about it, I guess, to get to the deeper meaning thing. So like not just accepting a squared plus b squared equals c squared, but like what?
Why?
Why? What is that?
They've got more than one approach to solving the problem.
Ah,
Flexible thinkers.
Angela?
They think about what's being asked, and what kind of math they can use to solve the problem.
In terms of what's being asked, like application kind of problems, and then applying mathematics to real world scenarios. Mary?
Making connections between different kinds of mathematics and how one thing that they already know connects to what they're doing now.
Just super challenging because we have units.
Mm-hmm.
Uh-oh. Oops, sorry.
Watch the clicker.
I thought I did the clicker. Karen?
They persevere, so they know that problems aren't always solved, generally aren't solved immediately. Stick with it.
Seems like it's in contrast to whoever said fast.
That was me.
For
Sarah?
the public.
It's hard being
Yeah.
the last one. Yeah, I said all. Confidence to make mistakes and play around with numbers.
Growth mindset. Cool.
Yep.
Well, we're gonna focus on three. I gotta jump around because I want to come back to something. We're gonna focus on three ideas of what were some core beliefs then versus core beliefs now. Like what were lingering core beliefs that have been around in the past that are kind of still being held true, both by parents, the general public, and kids. And then how has the research shaped our core beliefs? So that's kind of how the night is structured. We're specifically going to look at three, some of which were mentioned tonight, that there's this idea there's a best way. There's a one way that kids should solve the problem. Somebody mentioned algorithms. So kind of connected to that there's one best way. One that Angela kind of connected to, that there was a time, and there still is a time, where people really think learning math is all about memorizing. And then this last one is kind of connected to what Sarah said, this idea of being told that you're good at math. Yes. Okay. Is this idea that in math there are people who are math people, and then there are people, I'm just not a math person, is the third one. And so I just wanted to briefly connect it to this. People get a little bit queasy with change, and so I kind of want to connect it to this idea that you would not want to go to a doctor to have a high-stakes operation done if their medical practice looked like it did 50 years ago. There's more research that has come out. There are patterns that we've noticed in how the body works that have come out in the past, and there are new techniques with how to best work on human beings. And so in the same way, as practitioners of mathematics and teaching mathematics have new research and new changes, we would assume that just like the medical field has grown and changed, we too, as math instructors, should be growing and changing that, as we reflect on the research. And so don't get queasy. This is actually a good thing that math instruction has changed, though the math is the same, even though math instruction has changed. So I want to talk for my portion, which is going to be about 10 minutes worth. I want to talk about this idea that there is one way to solve a problem versus this idea there are many ways to solve a problem. And one of you mentioned this idea of flexible thinking, the idea to look at a problem from many different ways. And so this is a really common thought that's been around for a while. And if you looked at a textbook from 50 years ago, it would probably look at something like this. And kind of behind the scenes of this is this idea, this core belief that if they learn a procedure that they can repeat over and over and over again and practice it, then that will make it perfect, and then they can just use that procedure anytime. Sort of blindly, mindlessly, they can use the procedure. And so textbooks of the past had tons and tons of problems on a page, and they were very connected and related, so that you could then just learn those procedures and then apply them to any problem. And so what we want to talk about is how these are a third grade example, and we could look at any grade, but I picked one that was kind of a little bit in the middle. We noticed some changes. There are significantly fewer problems on the page. There are stories connected over here, word problems over here, and then I want to talk a little bit about what's going on this one. And so as we look at this, there's not an inherent strategy that is suggested by the kind of problem that they're giving, that you would just kind of keep crunching and crunching. This is application. So one thing that we're noticing is that there are many ways to solve a problem, and because of that, or that is because we really want to look at applying it to real-world settings. The other thing you'll notice
Bus 26 is here. Bus 26 is here.
This is kind of a standard textbook page. There's only 2 problems on this page total. Show 3 ways to make 41 cents using dimes and pennies. Show 3 ways to make 87 cents using dimes and pennies. This new textbook page is really reflecting this core belief that we really want kids to understand a variety of ways to solve a problem. And the reason for that is we want kids to actually spend most of their time paying attention to the numbers. So this is a definition of something that somebody earlier said, this idea of fluency or speed. But fluency, as we're defining it in math instruction, is beyond just speed. Speed kind of is that first green bullet. That for kids in math, we want kids to be efficient with their work. We want them to arrive at an answer in somewhat of a ready fashion. And we definitely want them to be accurate, which is one of the things that you said. But what we really want, in addition to those things, is for kids to pay attention to the numbers, because there might be a more efficient way with less chance for errors if you solved it in maybe a different way than a traditional algorithm way. An example that we gave to the
Nathan
parents.
Kessler, please come to the office. Nathan Kessler, please come to the office.
An example that we gave to the parents for this is this problem, 119 plus 119. I'm not going to have you all solve it, but we had them solve it, and we did a number talk, and we asked them how they went about solving this problem. And it was really fascinating to hear what they said, because some adults talked about solving it like this. 100 plus 100, and then 10 and 10 and 9 and 9 to solve it mentally, getting at that efficient, accurate, and just those 2, efficient and accurate. And so some adults kind of said, okay, and they walked through the steps of what they did in their mind here. Some of the adults did this notion of, oh, I could just look at it as 120 plus 120 minus 2. That was way quicker, and there were fewer places for me to make mistakes if I did it this way. And some people were like, oh, I would have never have thought to do that. And then at the end, as I recorded a couple of strategies, there was one parent who kind of like did this and said, didn't anybody else do it the old way?
Line them up on
Just
top of
and visualize it with her, she was like, I closed my eyes and I could picture carrying the one over like this. And then like 5 or 6 other hands went up, yeah, I did that too. And so for these people, some of them had this aha, like, oh, I would have never have thought of it this way. And that would be a lot quicker to do it. And there's less holding of number in head mentally when I'm doing something like this. And so we did that, and then we looked at student work, and we pulled up a bunch of student examples of kids doing the exact same thing. And that's actually when we talked about this, this is actually what we're looking for, is that students are attending to the numbers and the problems so much that they're able, and they have so many different strategies under their belt, that they're able to pick one that might be the most fluent, that might be the most accurate and efficient and flexible for that particular problem. And so for the classroom teacher, collecting assessment of student work might mean that you have a ton of different strategies, which my guess is looks a lot different than assessments in the 1950s did, where everybody was using one strategy, which the teacher thought was best. And so this is kind of this notion that there's sort of this lingering belief that there's an ought to. Oh, well, they ought to be doing it that way because I think that way is best. And so more experience with as adults where we're seeing other ways to solve that might be more fluent is kind of battling that ought to idea. And so I'm encouraging as many math teachers to have these kind of number talks with parents or send these kind of things home so that parents can see like, oh, I would have never done it that way. That would be way simpler to do it that way rather than just the ought to way. So kind of to wrap up this first idea of there's one way, there are many ways, I want you to just quietly read this, and then on the back of your paper, could you just write a keyword or a cluster of keywords, like a phrase of this is the research that is done around this, and then I want you to share it with a neighbor.
Jason Champney, please come to the office. Jason Champney, please come to the office.
All right, share with a neighbor. What were some key phrases in this?
I was gonna say, let's do it at the
Yeah, let's do it at the
table.
table.
With the chair. I'll go. Responsibility of learning was what that jumped out at me, and active, not passive.
I said fully engaged as thinkers.
Fully engage the thinkers. I kind of summed those up and said that the students are figuring out their best way.
Two things that stood out to me were each kid having an innate ability and turning responsibility over to their students.
Yeah, thanks for those thoughts. This idea that kids are picking up ideas from peers, that we're finding how to give them access to problems that are just at the cusp of their understanding, that push them to thinking a little bit further and maybe a little bit differently about problems, and that they're in essence doing the heavy lifting.
Buses 2 and 28 are here. Buses 2 and 28 are here.
So kind of the takeaway from this first big idea, this idea that we all approach problems differently. If I asked you guys today, like I did the parents, to solve this problem, my guess is we'd have a bunch of different strategies because people think about things differently. And we'll be doing that when we do a multiplication problem in a few minutes, really depending on the context, the numbers in the problem, and then looking at ways, how can I be most fluent when solving this problem? And you might solve it different if you have a pencil in your hand versus if you're doing it mentally. And then this idea that our instruction is shifting based on this core idea. We're encouraging students to look at the context. We're encouraging innovation and creativity because they might have a better way than we have. And then this idea that we're encouraging kids to grab on the strategies that make most sense to them because those are the ones that'll be the most deeply understood. So I'm going to turn the baton over to Karen.
So my big idea is that many of us used to think about math as memorizing. And while there are pieces of that remain in our curriculum and things that we want kids to do, really what we're focusing on is math as understanding, and that we want students to understand the math that they're doing. So take a minute and read this quote. Can you see around, Christian? So I loved the piece of the other quote that said, while we're performing mathematical stunts.
Mhm.
Because you think of, like, some kids really, it seems like magic. And so it's the same idea about moving symbols around on the paper. So take a minute and see if you can think about a rule or, a rule for moving symbols around that you learned maybe without understanding, that you memorized when you were in school.
All of them.
Got one? All of them? Everybody have one?
I have a really good memory.
Okay, so
therefore I
let's
was
just go
good at
around the
math.
table. What's one? Let's start with you, since you kept going last time. What's yours?
Oh, well, that's what I was just going to say. I was just going to say that most of my mathematical learning as younger was memorizing what numbers and symbols to move where. That's
Mhm.
and if I can memorize it, then I.
So do you know any
well.
tricks? Did you memorize any tricks or any phrases?
Yes.
Or?
Wait. My Aunt Sally, something about the order of operations, like.
Dear.
That was
My
the
dear,
planets.
my
My,
dear.
Oh,
my
no.
dear. PEMDAS?
No, that's
No.
long division.
No, not
My
that.
dear Aunt Sally.
It's something.
Just
Please
made me
excuse-
5
please
pizza pies.
Excuse my dear
Aunt
Just
Sally.
made me 5
Okay,
pizza
all right.
pies or something. No,
That's the
something else.
planet.
That's the
Oh my
planets.
Clearly it was
So our
connected
point
to
exactly,
understanding.
right? We remember something, but we can't put it to a context. Anna, how about you?
Like 238 minus 179, and you have to go and you have to like cross out the 2 and make it a 1, and cross out the 3 and make it a 12, and cross out the 8 and make it a, I think an 18. Yeah, an 18. I don't know, like why? Yeah, that.
So you just changed them and then
You
Now
cross
you
them
can
out
do
and
it.
you put a
cross
different
them out and
number
you
on
put
top.
something else there.
Yeah.
Invert and multiply.
Okay.
I know that one too.
Decimal moving for multiplication and division.
So what was
Still
the
got
what was
wrong.
the
You
rule?
count the number of places and you move the decimal place that number.
As long as you count right, then you're all
And you
set.
go the right direction.
Oh, there's a direction to it. Yeah.
Add a 0. That's my.
Add a
When you
0.
multiply by 10,
Mhm.
you just
Yeah.
add a 0. When you multiply by 100, you just add 2 zeros.
And you put a square around it so that you know that's a 0 that you added.
Didn't know that part.
Oh,
That
well.
trick
My,
either.
my
Maybe a
favorite,
little bit
my
later.
favorite is mine is not to question why, just
Just
invert and multiply.
No, I told
We
someone about
chanted that.
Guys, what is
Yeah.
the saying then for order of operation?
Please excuse my dear Aunt Sally.
PEMDAS.
Or please eat my
Did you ever get
What?
this butterfly?
Yes,
Butterfly.
Butterfly, and there was something too about there that actually the
Oh yeah,
plus,
I learned that.
the plus was like the intent.
Uh-huh.
You know?
Oh my gosh, kids are coming in now with the bow tie method for multiply.
Oh, the bow tie.
They didn't get it from us.
Oh
Just
my
so you know.
gosh.
So anyway, the whole point is that
Go on.
when I was in school, I was good at memorizing, and so I did well in math, and I actually took calculus, and I can't tell you anything about what calculus actually is about. And so what we're trying to do is it's okay if kids know some things like, please excuse my dear Aunt Sally, but why does that make sense? And what's the context, and can you relate it to something in real life? And if you can't remember, is there something you can go back to? So really wanting kids to understand, and part of that is just the joy.
Bus 22 is here. Bus 22 is here.
Grateful.
I know.
But like another piece is we want kids to enjoy math, and for some kids who are good at memorizing and can, like I was good at memorizing, so I could spit it out, and that was satisfying to me, but I wasn't learning. And we really want kids to experience insight and to have that aha and be excited about mathematics as a result. And
to keep it for longer than.
yes, and to give it, and right, and to remember actually what it connects to when someone asks you about it later. And the thing is, if many of us learn by memorizing, so if adults who feel like they're not good at math, it's probably because they weren't taught in a way that helped them to understand. So memory fades, understanding sticks. Anybody else with memory fades? All right, so take a minute and read this quote. So again, some of our work in math involves memorizing, but really we want kids to have these connections. And so one example is to think about, like, when you're at a large gathering or a party and you're meeting a whole lot of new people, how do you remember people's names? So think for a minute about whether there's a strategy that you use or a way that you help yourself remember people's names. Did it happen?
I don't, I'm gonna listen really carefully. Like, I
Because
have
it's
to go
really
back and
hard.
do the letters after, like, I'm like, who's that? Okay, A, B, C.
Ah,
Oh, really? That's a good story.
okay.
But I don't remember right away.
My
It's a
wife,
good thing we've said Sarah a couple times.
Yeah.
my wife and I threw a party this past weekend, and it was for all the people on our block. And so some we knew really well, and some we didn't know all that well. And so like right before they came, we put them into couples. You know, like the folks who were married, we would be like, okay, it's Bill and Amber. That's right. Okay, Bill and Amber, Bill and Amber. Okay, and then there's Vicky and Manny, Vicky and Manny, Vicky and, you know, and so like connecting them as a couple kind of helped the names stick together, as opposed to just sort of like random, isolated.
I make
Anybody
songs,
else have?
songs for everything.
You make songs.
Yes. I repeat it and then I make a little ditty in my head about their names.
Don't you want to do that for Sarah right now?
Well, and that's
The strength of mind.
but that's the alphabet, right? Like, how do kids learn the alphabet? From the song, because the alphabet is the letters are not connected to anything. It's a rote thing that you need to memorize. Anybody else with any great names, strategies?
I just try and connect something from them,
Yeah, somebody, there's a strategy. That'll work.
but make some kind of a connection. My sister's name is Anna, so I knew Anna's name right away. And so I just, okay, my sister, got it.
Or like a
Like
feature,
something that goes with, you know.
like Harry was Harry.
I don't do that because I'm afraid.
What'd you do?
Or it would be, yes, that's.
Or you might blurt it out when the number.
I know exactly. I called them the wrong.
Hi, Harry.
Yeah. So the point is the connection piece, right? If we can connect something that we're learning to something we already know, then it helps us to retrieve it. So this is where the carrots and potatoes piece comes from. And I think probably many of you have heard me talk about this before, but when we learn an isolated fact, it's like a carrot. So when you want to go get that information in your brain, you have to just go find it and pull it up. And if you've forgotten, you're just lost in the field and you can't find that piece of information that you're looking for. As opposed to if it's connected to something you already know or you've made sense of it in some way in terms of your own experience, then you can go there and pull it up. So like, for example, if I tried to memorize 9 times 7 is 63 and then I forgot and all I did was memorize it, I've got no way to get back to it, right? Whereas if I've forgotten what it is, but I can think about a strategy like, oh, what do I know about sevens? Well, I know 10 times 7, and I know that's 70, so if I take away 1 7, it'll be 63. Or if I really understand multiplication, I can think, okay, I could draw 9 times 7, and then I could look at my model and see how many things there are. So trying to think about ways to help kids connect, and this is building understanding. And there are a bunch of ways we do that. So one of the ways we do that is through models. So we could draw an array model or an area model for 9 times 7. Actually, I'll do that quickly. So we could draw a, so if the student is thinking about 9 times 7, and then they want to use 10 times 7, so this is the area, this is a linear measurement of 9 and 7. I could just extend that. So now this is 1, so 9 plus 1 is 10. So now I have a 10 times 7. 10 times 7 is 70. Whoops. And then I can cross that out, and I know 70 minus 7 is 63. So kids can go back to these models or these strategies, and that's building that understanding. Another way that we help kids build understanding as opposed to just memorizing is to put things in context. So one of the things that's difficult for kids often, and I just witnessed this actually in a 3rd grade classroom today, is going from multiplication to division. So kids are like, wow, we had 5 minutes of quiet time when kids had to try and figure out this division problem, and they sat there looking terrified because it's like fractions for middle school kids. It's like division for young kids. Like, oh my God, we have to do division. But if I'm thinking about it in context, which is what we did actually with the problem today, and we had kids use manipulatives. But if I'm thinking about, okay, so I have 12 yogurts, right? So I have 12 yogurts, and I know they come in packs of 3. So that's a context as a kid that I can think about. Maybe I've seen that or I could imagine it anyway. So I'm like, okay, how many packs do I have? Or how many in each pack? Sorry. My partitive quotative. Okay, so I can draw a model. I can imagine this. So I can say, okay, 1 pack of 3. All right, that's 3. I know I have to get to 12 yogurts. So 2 packs of 3, 6. 3 packs of 3, 9. There's another pack of 3. So I have 1, 2, 3, 4. So kids making sense based on what they understand about the situation. Make sense? Same idea works with fractions. So maybe this, probably most of you could figure this one out. But how about this one? So take a minute on your own. Think about how you would do it if you can remember. When I was taking a math class several years ago, I had to really think about what the strategy was for this. How could you figure that out? So this one was, how many 3s are in 12? So that's the question we were answering. How many 3s are in 12? So that might be another way in. Turn this around.
Elena Mack, please come to the office. Elena Mack, please come to the office.
Okay, so let's come back. With parents, I would have them turn and talk a little bit, and we'd go probably a little quicker to the solution, but you all are drawing lovely models and things, so we'll do that. What's our question that we're trying to answer with this equation? How many 1/2s? How many halves are in 1 and 3/4?
Bus 17 is here. Bus 17
So
is here.
what's a part of that that's easy to figure out? Where did you go first, maybe? How many halves are in 1? So how many halves are in this 1?
2.
Okay. So I know that this 1 is half plus a half. So I have 1/2, I have 2 halves. Okay. What else? Now what?
1/2 and 3/4.
Okay, we've got another half in there, so that's 3. And then what do we have left? Oh, which is a what? 1/4. So it's half of a half, so I have 3 and what halves? 3 and a half.
Bus 19 is here. Bus 19
Because this is half.
here.
1/4
buses
is
have been
half
filled.
of a half. So 3 and a half. Anybody do it with the algorithm? No?
Yeah, I ended up checking with the algorithm.
What is it again, Mary?
Mine is not to question why, I just invert and multiply.
So we would go 1 and...
First you need to make an improper fraction.
Okay, so which is... Wait, hang on, let me do it in a different color. 7/4 times 2/1, which equals?
Oh, I did both.
14/4, which equals? 7/2, or 3 and a half. Okay.
And that makes me say, what the heck does that have to do with anything? You know, like
Yeah.
that is totally devoid from meaning.
So the story problem that can go with this is if I have 1 3/4 cups of flour, and my recipe calls for a half a cup of flour. How many recipes can I make?
That is literally, I didn't drive a model says picturing my measuring.
Yeah. Yeah. So with
Yeah,
kids,
I
we'd
drew
start
circles and-
start with the story, and then go into. Kids have lots of different ways in. Some kids might think about this question. This question is really helpful, and other kids can just reason. You reasoned through this. I didn't give you a procedure for doing it. So the point is just that we want kids to be thinking about and making sense so they understand. If they can bring it back to a story context that makes sense, that's something that anchors them, so that eventually we are going to teach them the algorithm, and they're going to actually discover it through teaching, because that's efficient, like Christian was talking about, that efficiency piece. But if I forget what that rule is, I can go back to thinking it through or drawing a model or coming to a story context to help me figure it out.
You kids, I'm assuming this also, will probably get taught how those two connect, because right now, looking at that quickly,
These two?
yeah,
Mm-hmm.
they come to that too. Also,
Yeah.
Great.
Do you want to?
I know we
Yeah.
have to do it right now.
The
wanna
number
say more about
line
that?
is your best connector. The number line model, and we don't actually have to go all the way through it.
Yeah.
It's your best connector if you think about making a distance of 1 3/4 and how many halves are in there. You can actually see how many fourths those are. Anyway, you can actually, because it's 1 3/4, you can start seeing where your 14/4 are in that distance that then gets translated back to halves, which then gets translated into a mixed number.
I did that. That was my strategy. I also used the circles.
All right.
You know, the whole cut it in half and 3/4, and I saw a half there, a half there. There was another half, and then a half, a half, a half.
That's where it gets just kind of a commentary for parents to get that we're making sense of complicated mathematics in context was a big aha. And like, like our 4th graders could think about how many half cups are in there and really think about it. We don't have all these strategies yet, but they can make sense of the math, which is what we are going for.
The other thing that we talked about in this context, and we only have a couple more minutes, is just number talks. And I know several people at the table, if not every single one, have seen this number talk. So let's just quickly get some strategies for this one up here. So I'm going to give you a minute to think about it. We're working on accuracy, flexibility, and efficiency. So think about what would be your most efficient strategy for solving this. And this is a mental math activity. It's a number talk, and that's one of the ways this is different from some of the other things we do in classes. This is mental math, and it really gets kids to think creatively. So take a minute, and as soon as someone has one, I'll put it up here. Normally, obviously, in a number talk, we would give more time, but we need to just work it through. So Anna and then Angela.
I did 8 times 70.
That's what I did, so it only has to happen once.
So
Yeah. 8
having and doubling.
times 70. So you cut the 16 in half and doubled, and that is
560.
560. Anybody get a different answer than 560? I'm supposed to ask for answers first. Anybody have a different way?
I did 10 times 35. Sorry, I did 30 times 16 plus 5 times 4.
So 30 times 16.
Which would be 480.
Okay.
And 5 times 16 is 80.
And then what?
And then together.
All right.
Look, there was more than one way.
So we would continue on and gather as many different strategies as we could to think about how we can be flexible about doing this computation. And this gets to what Christian was saying too, that whatever the numbers are, if we can think about the strategies that are most efficient for solving a problem with those particular numbers, that's how we're being flexible, that's how we're being computationally fluent. And so as opposed to just doing the algorithm for this problem, which is the way most of us were taught and maybe forgot how to do.
And really hard to do when you don't have a pencil.
Really hard to do when you don't have a pencil. Yeah. So just in terms of big ideas for memorizing versus understanding, so we want kids to solve problems in ways that make sense to them. So strategies for manipulating numbers, using a model, using a story problem context, breaking up numbers into ones that are more friendly for them, things like that. And our instructions support this. We celebrate different strategies and make sure that those are made available to the class by putting work up and having kids deconstruct it to understand what that person did. We used to have kids come up and explain their work, but that gets everybody else in the class generally kind of zones out because it's that person's work, they're not that interested. Whereas if we put the work up and kids have to deconstruct it, they have to do some thinking and they may make better sense of the solution. So that's that selecting and sequencing piece. And then if we think about it, a lot of folks can do a lot of mathematics in their head, but they don't think of it as school mathematics. It's like something outside of mathematics. But we're trying to have kids think about that, think that way all the time, and so that the mathematics they would do in everyday life, like figuring out a discount on something, would be the same kind of mathematics they're going to do.
Keep getting 12 minutes. Okay, so this one I think in some ways for us as teachers challenges us more than the other. This idea that math instruction has changed. Then we believed you've got it or you don't. You've got a math gene. I certainly grew up thinking that there were people that had it and that there was like more powerful genes than others. Some people had like really good math genes. Some of us had like we're pretty good at math genes, and some research has shown again and again that we are all capable.
Bo Underwood, please come to the office. Bo Underwood, please come to the office.
That we are all capable of understanding mathematics. And what that means is we are all capable of understanding very complex mathematics. And that it's really in, the variables are in time and structure of how we learn math, but not in ability of some can and some cannot. For a long time, math instruction really looked at this bell curve. And this bell curve is based on that old belief that some people are just going to be at that lower end of the curve and are not going to be as able to learn the mathematics. Average people in the middle, you're going to have high average, low average, and then some people just kind of know it and get it. The model we're looking at now is really about this growth over time, where we're actually building understanding that all of us will get that. And then we have plateaus of understanding as we're building ideas, but that all of us are capable of understanding those concepts, given the correct given opportunity and time in order to develop those understandings and make those connections. You guys have done this in class, so I'm going to abbreviate this, but this idea that there are big ideas in mathematics, additive reasoning comes first. What we know about adding builds into multiplicative reasoning, which supports fractional reasoning, and as it goes up. That we have these learning progressions of big ideas, and that we can look at any particular place along the way where we can take one of those big ideas and take a look at a much more specific learning progression. We actually, fascinating, Christian. We'll have to look at that slide projection. I was like, where's the circle? There it is. We give this to parents. We have them take a look at it for a few minutes and talk about this is a learning progression. All of these strategies are multiplication strategies. They're just building towards more efficient and more generalizable strategies over time. The learning progressions are created by the research around them are looking at students that are developing these mathematical understandings over time. What are those connections that need to be made along the way in order to have that solid understanding and flexible, accurate, and efficient strategies, thinking multiplicatively. All students have access. This is that, I'm just unpacking. If you look at 8 times 14, some may draw all 8 groups of 14 and count them. Some could solve by making an area model, which we'll take a look at in a minute. And some may use an algorithm like the partial products algorithm. I very intentionally say the partial products algorithm, not the traditional algorithm, that there's more than one algorithm. Those learning progressions are develop over time. It's not linear. We're going to go up and down. If you can think about multiplying with whole numbers versus multiplying with fractional numbers and rational numbers, that moves into multiplying with variables. That we have this continuum that we'll be able to build an understanding that we'll have to go back to some modeling as we're learning a new number set, as we're developing more complex ideas over time. I have all the parents solve this. You guys have actually done this, and then we're going to look at some student work.
Oh,
no, I actually asked them to solve it like they would.
Yeah.
So that they now have an accurate solution, so they can now look at student work compared to the learning progression.
And they can look at their work, right?
They've got their work and
Which
student work.
we would have, you know, the parents do, but for you guys, just looking at this and knowing the progression and the continuum, can you think about what strategies where the student would follow the learning progression? Maybe once you know, we could talk as a table or with your neighbors or small group.
These guys know this fairly well.
Yeah.
So where are we, guys?
Okay, let's do it.
Transitional.
Yeah, it's transitional, and then how about here? What do you see? What do you notice? Yeah.
I know they're paying attention to like the value of the numbers. That
Partial products. Yeah, and it's the partial products, but without they're envisioning in their brain the area model. So they are the same products. And then, how about this one?
And actually more efficient, because you're not writing out all of those equations, right? And so it's evolving.
Interesting how those signs are on. That throws me
Yeah.
You just never know what you're going to get.
Yeah. So this is Mary, the partial products algorithm. Yep, and the movement for that.
So the other piece is this idea of, and this is a big important piece for me with parents, this idea that models are not just for those that need them. Models are a piece of mathematics that should be part of all of our instruction. We need to think about how our language changes around that. You know, if you need to use a model, go ahead. But then that implies that you shouldn't need to, or maybe sometime you won't need to. And actually, mathematicians use modeling all of the time. It's a major part of thinking mathematically. And so that message of a model being an important tool for us as mathematicians doesn't go away. So I actually asked parents to take a look at this and to solve algebraically. And there's a lot of angst to begin with. And I've got it on the chart paper. So anybody just want to give it a shot? How can we use that same area model thinking towards this strategy? Who feels confident about a piece of this?
Okay, I think 6x squared, is that the first section? 3x times 2x,
Is 6x squared.
right? 9x.
8x below.
And when we think about this idea of having 8x plus 9x plus 8x plus 12, and then combining like terms, getting to that factoring of a quadratic equation, and being able to see this connection through the use of a visual model helps bring that connectedness of that mathematics to a higher level. And they can build on something that they already know and understand to develop a new understanding. And that It's not about having a mathematics gene. It's about having those opportunities to make the connections between something you already know and apply it to a new and novel situation that is still multiplication with just a different set of factors that we can think about and look at differently.
This still also attends to the fact that when students use this model in the primary grades through third through fifth for basic multiplication, it's not a trick.
Right.
Because it also, we could model this with fractions or decimals, and then we can model it with variables. And so it's a model that is doesn't expire. It satisfies through all grade levels, mathematically accurate.
And it's robust, but then becomes because we don't know what X is, it's now modeling mathematics, but not necessarily modeling an accurate area, because we know X could be like -2. And thinking about what that would then look like, we could put it on. Okay. All right, so the big idea is this idea that there are progressions of learning in mathematics that are based on math ed research, that we as educators now know about how the brain, not just what mathematics we're teaching, but also how the progression of that learning occurs. Our instructions support this by analyzing student thinking and building on what they know. We're providing explicit instruction towards more efficient strategies and connecting strategies along the way. And that core belief that all students are capable of learning mathematics, not just those with the math gene, because we all possess that math gene. How can we help find that within all of our learners? We talk a little bit about this cycle of learning that we're teaching, assessing, analyzing, and adjusting instruction based on the developing understandings of our students on a regular basis. And I'm going to pause. And then we do ask for an exit question to talk about what is one of those new ideas that you've got from this thinking to take away. One of the things that we don't do that's important is that we do not have a question and answer session. Those questions and answers need to go to the teacher and the parent. Our role as coaches, and this is for us as teaching staff, our role is not to replace that relationship between parent, student, and teacher. It's to give this overview of broad changes that have happened in mathematics and education that can then be dug down deeper within their own setting and classroom. And
Can you be
direct
there when they
parents
ask
there.
us the question?
Yes, I'm happy to come and be part of any of those conversations. Yes.
And just to feel like you have the safety to say, like, let me think about that and get back to you, you know, and then email one of us.
Yeah, absolutely. Okay. So we're hoping that we'll have a number of parents. A lot of the parents came from the Jericho area because that's where it was held last time. So we're having a parent night in this area to see if there are people that have questions and concerns. They can come take a look.
Mhm.
Thank you. You're welcome.
Thank you.
Thank
for
you.
coming.
Thank
Thanks
you.
for coming.
Did you guys have?
Mhm.
You talked about that research you told us the other day with, like women in particular saying to their daughters.
So
I'm not gonna ask your
one of
dad.
my goals is not to make people mad.
It's true.